In the last several videos, we looked at a variety of electrophilic aromatic substitution reactions, which all allowed us to replace one of the hydrogen atoms on the aromatic ring with some sort of electrophile. Now what we're going to focus on in the next several videos are modifications that we can make to those groups that we have bonded to the aromatic ring. And we're going to, in many of these reactions, be focusing on a common theme of reactions that occur at the so-called benzylic position. When we refer to the benzylic position, what we are always discussing and describing is the atom that is directly connected to the aromatic ring. And so in the structure that I have just drawn here, the carbon that I'm drawing an arrow to would refer to the benzylic carbon. Hydrogens that are attached at that position would be referred to as benzylic hydrogens. So if we had a CH3 group here, we would refer to each of those three hydrogens as our benzylic hydrogens. In order for the atom to be described as benzylic, it has to be directly attached to the aromatic ring or hydrogens that are connected there. So we have a benzylic carbon and three benzylic hydrogens at this position. If the group is further down the chain, it is not going to be benzylic. Benzylic is specifically referring to the position that is directly attached to the aromatic ring. And the reason why we have a special name for this position is there are a variety of special reactions that will go on at this location of the molecule. And one such reaction, or two such reactions I should say, are the Wolff-Kishner and Clemmensen reduction reactions. That is what we're going to focus on in this particular video. In both the Wolff-Kishner and Clemmensen reduction reactions, which are named after the discoverers and developers of the reaction, what is going to happen is that we start with a molecule that has a carbonyl group at the benzylic position. This will be a ketone group. So we have a keto group where the carbonyl is directly attached to the aromatic ring. In other words, it is a benzylic carbonyl group. And using the specific reactions required for the Wolff-Kishner reduction or the Clemmensen reduction, what we are going to do is reduce the carbonyl group all the way from that carbon-oxygen double bond to carbon-hydrogen bonds. So we're going to go from a carbonyl group at that benzylic position to a CH2 group as a result of this reaction. So this is a useful way for going about creating a product that has a carbonyl group at the benzylic position and then reducing it to an alkyl group at that position. So let's next take a deeper look at these two reactions by evaluating what reagents are necessary for creating this reduction reaction, and what situations Wolff-Kishner would be preferable versus what situations Clemmensen would be preferable in, and what are some situations in general where we would need to use the Wolff-Kishner and Clemmensen reduction reactions in the synthesis of organic molecules. So taking a look at the reagents required for each, I'm going to draw in here my starting structure for my Wolff-Kishner reduction. And I'm going to put R in here as R is equal to an alkyl group. So we absolutely have to have a carbonyl group at that benzylic position for this reaction to work. What will happen in the Wolff-Kishner reaction is that we mix our starting material, our acylated aromatic molecule here, with a mixture of hydrazine, which is H2NNH2. The fact that it has that nitrogen-nitrogen bond makes this relatively reactive. We refer to this structure that I've just drawn as hydrazine, so that's another way you might see this written out. And the other reactant that is present here is a base. Specifically, generally it's potassium hydroxide. So you have potassium hydroxide plus hydrazine, and what that is going to do is result in the replacement of the carbonyl group at that benzylic position with hydrogen. And so we go from the carbonyl group in the starting material, right here, highlighted in blue, to a CH2 group in our final product. We are not going to go through the mechanism for this reaction. It is a bit beyond the scope of the class and a bit beyond the length of time that we have available to discuss these things, but you should be able to recognize and apply this reaction in that if you're trying to create a targeted organic product, you should be able to tell me what the starting material you would need to use in order to accomplish that through the Wolff-Kishner reduction. Or if you were given a problem where we were missing the reagent here, you should be able to fill in what you would need to use in order to convert the carbonyl group here at the benzylic position of the ketone into the alkyl group, the reduced molecule. So that's our Wolff-Kishner reduction. Be aware and able to apply the reagents that we are using here in the Wolff-Kishner reduction. So what about the Clemmensen reduction reaction? So in the Clemmensen reduction reaction, similarly, we will start with our acylated aromatic ring here. Again, the R group is an alkyl group. In the Clemmensen reduction reaction, though, rather than using a mixture of hydrazine and potassium hydroxide, what we are going to use is an amalgam, a mixture of zinc and mercury. I'm showing that it's an amalgam by placing one of the substances into the parentheses here, indicating that we're using an amalgam of zinc and mercury. Additionally, we use hydrochloric acid, HCl, in this reaction mixture. And the outcome is going to be the same as what we saw in the Wolff-Kishner reaction, that we reduce the carbonyl group that we saw here to a CH2 group in our product side of the equation. And that is accomplished using this specific combination of reagents, zinc, mercury, and hydrochloric acid, HCl. So why do we need both of these methods? They seem kind of redundant of one another. Both are ways that we can go about converting the carbonyl group at the benzylic position into a CH2 group. The reason why we need both of these in our smorgasbord of reactions is because if we are working with a relatively complex organic molecule, bases and acids have a variety of different functional groups that they react with, and we would want to be able to avoid undesirable reactions. You'll notice that the Wolff-Kishner reduction involves a base, potassium hydroxide here, versus Clemmensen has hydrochloric acid. And so if you are doing a reaction, you will want to look at the other functional groups that are present in the aromatic molecule and ask yourself, would any of those groups react with a base? If the answer is yes, they would react with a base, then you may want to avoid the Wolff-Kishner reduction, because the Wolff-Kishner reduction would likely result in a reaction of that base with whatever group you were looking at that was reactive with base. On the other hand, the Clemmensen reduction reaction, you would want to avoid those conditions in the event that you were working with a compound that had a functional group that was susceptible to reaction with HCl. So to give you an example of applying this concept toward a problem, let's say that we started with the following aromatic molecule. We are going to say we're starting with this particular compound here. And we wish, in this reaction, to selectively reduce the carbonyl group to a CH2 group without disrupting our alkene group over here. So we want to convert this carbonyl group that I'm highlighting into the CH2 group over here without disrupting this group. We want that group to stay the same. And so I could give you a question where I ask you, what reagent or reagents would you need to fill in here in order to do that? In order to decide what to use here, Wolff-Kishner or Clemmensen, to carry out this reduction reaction, you have to think about what types of reactions do alkenes undergo. And a main type of reaction that alkenes undergo is alkenes are subject to addition reactions with electrophiles. And one common electrophile that alkenes can undergo addition reactions with is HCl. And so, therefore, if we want to keep that alkene group intact, we need to avoid a reagent that has HCl. And so that means that we can't use the Clemmensen reduction. Don't use the Clemmensen reduction. Instead, use the Wolff-Kishner reduction because our hydrazine and our bases tend to carry out elimination reactions. We don't have any leaving group here in order to carry out an elimination reaction. So our alkene group is not going to react with that KOH base. And so we can safely use our our Wolff-Kishner reduction reaction mixture in order to carry this out. So we put in potassium hydroxide, hydrazine, H2N, NH2, and that would carry out this reduction reaction, enabling us to selectively reduce the carbonyl group to a CH2 group without affecting the alkene group down here. As another example, let's tackle the problem here and ask what would be the appropriate method for reducing our starting structure to a CH2 group here on this side in our final product. So how do we go about doing that? We have to think about what functional groups we have in the molecule and whether they are going to be reactive with our acid or our base to avoid undesirable reactions. So we have a chlorine atom here. Chlorines are good leaving groups and very subject to elimination reactions. And in an elimination reaction, such as an E2 reaction, what happens is that a base comes in and removes a proton at the beta position, forcing the leaving group chlorine to leave, and using Zaitsev's rule, we place an alkene group into the molecule. So since this group is subject to an elimination reaction, specifically under basic conditions, we don't want that elimination reaction to take place. We want to remain and retain the chlorine atom here. And so in order to accomplish that, we need to avoid using the Wolff-Kishner reduction reaction because the Wolff-Kishner reduction has that potassium hydroxide base that would result in an elimination reaction. And so instead what we use is our Clemmensen reduction reaction mixture. So take our mercury and zinc along with our HCl, and this reaction is going to progress as desired because the mixture of zinc, mercury, and HCl is not going to affect our chlorine atom here in the molecule. So you'll want to keep this in mind when you are working with the Wolff-Kishner or Clemmensen reduction reactions, that the specific reduction method you choose should be dependent upon what other functional groups are present within the molecule. If there are no other functional groups that are susceptible to acid or base reactions, then you don't need to worry about it. Now let's do another synthesis reaction that will illustrate to us an additional application of the Clemmensen reduction or Wolff-Kishner reduction in organic synthesis. So in this problem, we are tasked with starting with benzene and ask how would we go about, what reactions would we need to carry out to create a product that has this isobutyl group bonded to the aromatic ring. And so thinking about how to go about doing this, one thing that you might be tempted to do is you might say to yourself, well, I remember Friedel-Crafts alkylation, where we took our starting structure, we reacted with an alkyl halide, such as isobutyl chloride, and aluminum chloride catalyst. And out of that reaction, we would replace one of the hydrogen atoms on the aromatic ring with the alkyl group. But the problem with that reaction, the Friedel-Crafts alkylation reaction, is that carbocation rearrangements are possible. And so the problem with the reaction, as I've written it out here, is that you would not actually get the desired product that we see up top here. Because what would happen is that during the course of this reaction, if we think back to the mechanism, what would happen here is that our chlorine from our alkyl halide reacts with the aluminum chloride catalyst. So lone pair comes over, forms a bond to the aluminum. that results in a chlorine bond to the aluminum of the aluminum chloride catalyst. Negative charge on the aluminum, positive charge on the chlorine. And then what happens next is that as the leaving group chlorine is breaking away to form a carbocation, since simply breaking this bond here that I'm highlighting and showing the electron pushing arrow in blue for would create a primary carbocation here, simultaneous to that we have a carbocation rearrangement to stabilize the molecule as much as possible. And in this case, the 1,2 shift or carbocation rearrangement that would occur would take this hydrogen, bring it over one spot as the leaving group is leaving, and that would result in the formation of a stable tertiary carbocation out of this reaction. So you would end up with, by moving that hydride over, you would create a CH3 group right here where I'm highlighting that CH2 group that the leaving group is left from would become a CH3 group by having this hydride shift over. As a result, you would have a tertiary carbocation, and then what would happen from there is that tertiary carbocation would be what is attacked by the aromatic ring. And so as a result, the electrophilic aromatic substitution product would not have the isobutyl structure anymore. Instead, that would have rearranged to a tert-butyl structure. And so therefore, this Friedel-Crafts alkylation reaction would not work for giving the desired product here. So this would definitely not yield the desired product. And the reason it won't yield the desired product is because of that carbocation rearrangement. So if you're in a situation where you would like to put something like an isobutyl group on here, a group that would be subject to a rearrangement during Friedel-Crafts alkylation, if you want to attach that to the aromatic ring, here's how you can go about doing it. Using the Wolff-Kishner or the Wolff-Kishner reaction as a main step to that. So let's draw out our product first here. We're going to think backwards in this synthesis problem. So in this synthesis problem, if our final target product is what I am circling in blue here, and we want to take logically one step back and we want to say, how can we make this via Wolff-Kishner, which I'll abbreviate as WK, or Clemmensen? How would we go about doing that? Well, the starting material that we would need to use for that reaction is that we would have a carbonyl group at the benzylic position right here. And by treating with the Wolff-Kishner reagent or the Clemmensen reagent, that would result in reduction of that carbonyl group to the CH2 group that we see in the final product. And so in order to accomplish that using Wolff-Kishner, we could use potassium hydroxide and hydrazine, H2NNH2, or if we're using Clemmensen, we would use our zinc, mercury, Hg, amalgam with HCl. Either one of those will work, and we don't really need to worry about which one to use because we're starting with an aromatic ring that has no other substituents on it to worry about. So now from here, thinking backwards again, we ask, is there a way we know to get from an aromatic ring to this substituted aromatic ring? Since we're trying to start from benzene and move forward to the end here, is there a way to go from benzene to this? And indeed there is. Let's use one of the reactions that we learned about in an earlier module, Friedel-Crafts acylation. That reaction is awesome because it is not subject to carbocation rearrangements. And so, therefore, what we can do here, not worrying about carbocation rearrangements anymore, is we can draw out the group that we wish to attach to the aromatic ring here in blue. That is our acyl group. Acyl group in blue. And then the halogen that it was bonded to is the halogen right here. And so our Friedel-Crafts acylation results in replacing that halogen with the aromatic ring. And the catalyst for that reaction, which we absolutely have to put in there, the reaction will take a lifetime to occur, is aluminum chloride. So I plug in the aluminum chloride catalyst, my acyl halide, and we are good to go here. And so this reaction that I'm showing at the bottom that I have just circled would be our way to go about answering this question up top here of what can we use to convert benzene into the desired alkyl substituted benzene product. And we have to use this two-step series this time of acylation, followed by reduction of that acyl group to an alkyl group, because we can't directly attach this alkyl group onto the aromatic ring without a rearrangement taking place. So this is one of the main uses of the Clemmensen and Wolff-Kishner reactions, is that it gives us a route to creating alkyl substituted aromatic rings without rearrangements being a problem.